Okay, you guys, today we're going to talk about solubility and pH. So this directly relates to the ideas that we're starting to work into with regards to how stuff interacts with water and then how that impacts all of us living things on the planet. So please take out your notebook, go ahead and give your notes a title, and we will get started. So water often gets called the universal solvent. And what this means is that water dissolves a lot of different types of stuff. So water can dissolve many different substances. Water molecules are polar, as we learned last quarter. And that allows them to interact with other polar substances to dissolve them. Water molecules act like little magnets. We talked about that. And so they like to interact with other molecules that are also little magnets. And thinking back, we can recall that ionic compounds are essentially just very, very polar compounds, right? They've become so polar that instead of sharing electrons unequally, one of them just takes all the electrons. Not all of them, the valence electrons. So let's do a little critical thinking here. How do ionic and polar covalent compounds dissolve in water? Consider images A and B. What do the delta plus and the delta minus indicate in image A? So I'm talking about right here on this little green and gray guy. What do you think the delta plus, so it looks like a cursive D or an incomplete 8 or something, and delta minus, what do you think those indicate? Those indicate our partial charges. And so that tells us that the gray side is a little bit positive, and the green side of this molecule is a little bit negative. What do you see that's similar between images A and B? What are some differences, or at least one difference, that you notice between A and B? So hopefully one thing that you notice that's the same is that water is surrounding the things that are not water. So this green and gray guy is surrounded by waters. So is this one, so is this one. And then if we look at image B, we can see that the ions, the parts of the salt crystal, get surrounded as well. So the negative ion gets surrounded by water and the positive ones get surrounded by water. The difference is that in image B, the salt is getting broken up, right, into individual ions or individual atoms. But in image A, the molecule, the green and gray molecule, stays together. So the charges associated with water's polar covalent bonds attract it to ionic compounds and polar molecules. We know that the oxygen side of water is a little bit negative, and so it attracts things that are positive or a little bit positive. And the hydrogen side of water is a little bit positive, and so it attracts things that are negative or a little bit negative. So they're really all just acting like magnets. And what that means is you can see that this negative oxygen is kind of attracted to the partially positive part of the green and gray molecule, and the positive-ish hydrogen is attracted to the negative-ish green part of the molecule. Same thing over here. We can see all the little bit positive hydrogen sides of the water molecule are facing the negative ion, and all the little bit negative sides of the oxygen are pointing towards the positive ion. And so they're just acting like little baby magnets. All right, so I want you to think about the image below. I don't know why it starts at number 2, but that's all right. What do you think? Based on this picture, what do you think hydrophilic and hydrophobic may mean? So if we look at this, we can see that hydro is maybe referring to water. We often talk about hydration or hydrology or hydrosphere. So it's something to do with water. And in picture A, all of the water is mixed throughout the molecules that are different than water. But in image B, all of the molecules that are not water are grouped together and they're not mixed in with the water molecules. So hydrophilic is saying that we're mixed in with the water, and hydrophobic means that it does not mix with the water. And we know that phobic comes from or is related to phobia. We know that like a phobia is like a fear. So you can think of this almost as the molecules are afraid of the water. So they're staying together with each other because they don't want to mix with the water, because they're hydrophobic. Which image, A or B, shows a substance that is dissolved in water? And how do you know that? I would argue that A shows something dissolved in water because all the molecules are surrounded by water molecules, so it's evenly dispersed throughout. But in B, the molecules that are not water are close to each other and they're all grouped together. So those are probably not dissolved in water. You'll also notice that this molecule is perfectly symmetrical and it does not have partial charges. And for that reason, it doesn't dissolve. So why do you think that is? Hopefully it makes sense to you that the waters would be much more interested in each other because they are all tiny magnets than they are in this molecule that doesn't have a magnet at all. They're like, well, I just don't find you very attractive because you don't have a partial charge. And so the waters are more attracted to each other. So they just hang out with each other instead of with these nonpolar molecules. The other part of this phrase, the universal solvent, we know that universal comes from the idea that water dissolves a lot of different types of stuff, but solvent is a word we use to say that something is able to dissolve other substances. So water isn't the only solvent. Many solvents exist. Many different liquids can be solvents. But water is that universal solvent because it dissolves so many ionic and polar covalent compounds. This can be a good thing, and it's part of what allows life to exist, but it can also be a really bad thing. So we're going to explore that. Why does solubility matter? Pros of solubility: it's a really important molecule because the molecules for life are all water soluble. So oxygen and carbon dioxide are water soluble. Salt, electrolytes, minerals, things that help our body function are soluble in water. Sugars are soluble in water that give us energy. On the flip side, a lot of toxic pollutants, which could be chemical or biological, are soluble in water. So heavy metals like lead, which is poisonous, inorganic compounds, so things that don't come from living things but can be really toxic, organic compounds, which might come from living things, or contain just non-metals. Those can be toxic. And then acids and bases can be really dangerous as well. They can also be good, but they can also be dangerous. So let's talk about this acids and bases business a little bit. Maybe we've heard something about these. I think acids are probably what we talk about the most commonly. And an acid is something that makes a hydrogen ion when it's dissolved in water. So it makes an H+. Some examples would be hydrochloric acid or carbonic acid. And the name comes from the Latin word acidus, which means sharp or sour. And if you think about vinegar, which is an acid, or citrus fruit has citric acid, so like licking a lemon, right? Those tend to be kind of sour or sharp. Other types of food have other types of acids, but there's more sugar to balance them out, and so we don't notice the acids as much. So the more H pluses, the more acidic. Since an H plus is what makes something acidic, if you have more of them, it's more acidic. Here are some things that an acid does. It tastes sour, it conducts electricity, it's corrosive, which means it breaks stuff down. So acids can corrode and break down fabric or skin or paper, sometimes even metals. There's acids that react really strongly with some metals. Acids are super useful though. Acetic acid is vinegar, which we use for a lot of different stuff. Citric acid, also useful and delicious. Ascorbic acid is vitamin C, and your body needs that to function, so it's kind of a big deal. Sulfuric acid is used in a lot of production and manufacturing of fertilizers and steel and paints and plastics and stuff that we use kind of day to day. Car batteries, think about battery acid, that's important. Bases are equally important, though they tend to kind of fly under the radar. A base is a substance that produces OH minus when dissolved in water. So OH is a molecule called hydroxide. And so some examples of bases are sodium hydroxide, potassium hydroxide, and if a solution has an excess of OH minus ions, it is a base. If you have more OH minuses, it becomes more basic, just like more H pluses made it more acidic. Another word that we use for base is alkali. So you may hear alkali sometimes. I don't use that very often, but other people in the world do, and it just means the same thing. It's base, it makes OH minus ions. Properties of bases include that they feel slippery, they taste bitter, they're corrosive, they can conduct electricity, like an alkaline battery, right? There's that word alkali. And then they don't react with metals, which is kind of different from acids. Bases are actually super useful as well. They give soaps, ammonia, and other cleaning products their useful properties that allow them to clean things. And the OH ions interact strongly with substances like dirt and grease and allow us to wash them away. Chalk and even oven cleaner are examples of products that contain bases. And remember, not all bases are equally strong, just like not all acids are equally strong. Some acids, like citric acid, that's okay to consume or be exposed to. But you wouldn't want to be exposed to sulfuric acid. And so chalk is another example, like that's a base, but it's not really like dangerous to you. Whereas oven cleaner can be a little bit more on the dangerous side. And so it's important to know that it's not the acid or base that makes something good or bad or dangerous or safe. It just depends on which one it is. So how do we measure or describe how acidic or basic something is? We use the pH scale. Pause the video, draw this in your notes, preferably with color because your brain loves color. So you've got acidic, 0 through 7. And then alkaline is 7 through 14. And neutral is right at 7. pH is a measure of how acidic or basic a solution is. and it ranges from 0 to 14.